In this lesson, we're going to look at nuclear power. The first aim is to explain the processes of nuclear fission and nuclear fusion, then explain and evaluate the use of nuclear power stations, and then evaluate the use of nuclear fission and fusion as a source of energy. Now, I don't think anyone welcomes the idea of nuclear power with open arms. Nuclear power represents one of humanity's greatest fears, and this is evident by what we see in films and video games and so on, where we're presented with a bleak vision of the future as a result of nuclear power going wrong. And the truth is, if nuclear power did go wrong, it's true, catastrophic things happen. We don't have to think too far back in terms of our history to understand this. Firstly, in the Ukraine, we had the Chernobyl disaster, and more recently in Fukushima in Japan, we had another nuclear disaster. So why do we even persevere with the idea of nuclear power? There must be some great benefit to it. So hopefully today, I hope we clear up some of the myths and skepticisms that go with nuclear power and also understand the real dangers. Nuclear power is called so because we are literally looking at the power of the nucleus. You see, inside every atom you have a nucleus, and the particles that make up a nucleus are bonded together by an extremely strong force. In fact, the force is called the strong force. By breaking the bonds that hold these particles together, we can release lots of energy, more than pretty much any fuel you can think of. There are two ways in which we can unleash the energy stored in a nucleus, through nuclear fission and nuclear fusion. Nuclear fission is literally when we split a nucleus apart. A fissure is a crack in the ground, a split in the ground. So hopefully that'll help you remember what fission is. It's when we split a nucleus apart. But not just any nucleus. We use a specific isotope or radioisotope called uranium-235. That means a uranium atom with a mass of 235. Now, like all radioisotopes, this isotope is very unstable. The nucleus will eject matter to gain stability. Uranium is very readily available in our planet and very cheap, so in some ways it's an ideal fuel source. But how do we get energy from uranium-235? Well, it starts off with a neutron, that subatomic particle we find in the nucleus. Firstly, a slow-moving neutron is fired at a uranium-235 nucleus. This causes the nucleus to become unstable, and it causes it to split. It's very important that that neutron does travel slowly. If it was to travel quickly, it would pass right through the nucleus and not be absorbed by it, therefore the nucleus would not become unstable and not split. Upon splitting, two daughter nuclei are produced, and also a lot of thermal energy. By that I mean two smaller nuclei are produced. You can see that these nuclei are about half the size of the original one. But also 2 or 3 neutrons are released which can hit other uranium-235 nuclei. So these neutrons were part of the big nucleus, and on splitting it they become loose and free to move on. Now what can happen is these neutrons go on to collide with other nuclei. This causes them to become unstable, and subsequently they split as well, and the process continues, as more neutrons are released to carry on this process. And of course more thermal energy will be released, and after all it's the thermal energy we're interested in. So these ongoing collisions cause a chain reaction. That's a key term. And often in exams you're asked to describe what happens during a chain reaction, and this is what you would say, so it's worth committing this to memory. It will usually be worth about 3 marks. Now, a chain reaction can be a very dangerous and scary thing. If it's left uncontrolled, it can result in an explosion, as an increasing number of nuclei gets split and more heat gets released. The reaction gets exponentially larger. But we can control it in 2 ways. Firstly, we use a moderator. That's a fluid in which the uranium fuel rods are placed. And what this does is it slows down the neutron, ensuring a steady rate of fusion. So we already know that that neutron has to be moving slowly, but it gives an element of control, as it doesn't mean that we're getting constant bombarding of neutrons against these nuclei. Secondly, we can use control rods. All nuclear power stations have control rods, which are usually made from boron, just like the moderator is usually water, but both these things can be slightly different in exams. Go by their names, control rods and moderator. That's how you get their function. Control rods are raised and lowered to absorb excess neutrons and control the reaction. So as you know, when they split, they release more and more neutrons. So by lowering control rods, they absorb these neutrons and stop the chain reaction. And this is the big joke in The Simpsons, because it's essentially Homer Simpson's job to be in charge of nuclear safety, in other words, controlling these control rods to prevent a chain reaction and an explosion. And obviously the joke is someone with such low intelligence probably shouldn't be in charge of something so dangerous. You will need to know how nuclear fission reactions are controlled using these two methods, so it's worth jotting these down and committing them to memory. Nuclear fusion, by contrast, is how stars, such as our Sun, make their energy. Fusion is the exact opposite of fission. Instead of splitting nuclei, we are smashing them together so they stick together. So small nuclei, such as hydrogen, collide and join to create larger nuclei, which also releases thermal energy. So here I have two different isotopes of hydrogen. If I can get them moving fast enough, they will collide and combine to produce a larger helium nucleus and lots of thermal energy. The problem with fusion is that all these nuclei have a positive charge, so when you bring them next to each other, they'll want to repel each other strongly. So to overcome this repulsion force, you have to heat these particles up to such a temperature that they smack without repelling each other. This is why fusion is generally only possible in the cores of a star where it's hot enough. The ideal fusion temperature is about 10 million degrees Celsius, to give you an idea of the heat we need for this to happen. However, some scientists claim that they've carried out nuclear fusion at room temperature. This is something we call cold fusion, and we are very interested in the idea of cold fusion, as it could solve all the energy problems we have. However, whenever the experiment has been repeated by other scientists, we have not got reliable results. In other words, we don't always end up with the same result. The original study for cold fusion was not peer-reviewed and basically became public before being checked by other scientists. And for these reasons, this work was rejected by many scientific journals. They refused to publish it because they didn't feel it was reliable enough. So because these results were unvalidated, the theory of cold fusion is currently rejected by the scientific community. It may sound harsh, but it's the only way that we can ensure that the results we get are true, they're meaningful. And this embodies the very nature of science, to state what is true based on evidence and nothing else. So that is how we explain the processes of nuclear fission, splitting the nucleus, and nuclear fusion, combining the nucleus, both which release thermal energy. So how do we get energy from nuclear power? Well, we use nuclear fission. That's what a nuclear power station does. But if you remember, generally what happens in a power station is we use some sort of fuel source like coal, oil or gas, we heat it up and that boils water which creates steam, the steam turns a turbine, the turbine drives a generator which produces an alternating current. All a nuclear power station does is replace a furnace with a nuclear reactor. So in our nuclear reactor we have uranium fuel rods, so neutrons will be released and will bombard into the next fuel rod. And the control rods will be lowered in between them and raised to control the fission reaction. Surrounding the fuel rods is a coolant. It's a liquid that will basically allow heat to be transferred to it. It absorbs heat, heats up, and therefore boils water in a pipe which turns to steam. So fission releases heat, the coolant heats up and boils water. The steam turns a turbine, which drives a generator to produce an alternating current. Sometimes in exams you have to explain how nuclear power stations work, and this is what you'd have to say. Do look out to see if they actually want you to explain how nuclear fission works as well, because then you'd have to combine it with the previous explanation. So nuclear power does require a close look. We really need to examine the for and against arguments, because there are good arguments on both sides. I'm going to start with the negative this time. So radioactive waste is difficult to dispose of, and this is one of the biggest issues. Currently, we use a process called vitrification. This is where we put our spent fuel rods in some melted glass and put it into a steel drum. The glass then solidifies, containing the fuel rods. We then bury it deep underground and cover it to make sure it's out of harm's way. Basically, you want any sort of thick container, thick layers of concrete and lead, something which will absorb that radiation and stop it leaking out. The other issue is the waste has very long half-life. Now, if you want to understand that, watch the tutorial on half-life. But the waste remains radioactive for at least hundreds of years, sometimes thousands, sometimes millions. For this reason, the waste needs to be put far away from humans. Now, because humans colonize pretty much everywhere on this planet, that's not as easy as it sounds. Setting up a nuclear power station, because of the risks involved, is very, very expensive. but not quite as expensive as decommissioning a power plant. To actually take down a power plant safely and securely takes decades. And let's not forget everyone's greatest fear, which is the risk of nuclear meltdown. That's when an explosion sends radioactive dust hurtling through our atmosphere, spreading miles away from its source, and causing all sorts of problems, some of which last generations. You may have seen pictures of mutated animals and mutated humans as a result of this radiation fallout. Definitely scary stuff. But why do we even entertain the idea of using nuclear power? There are some very good reasons. Well, firstly, nuclear power has been used a lot, and even the UK uses nuclear power. You don't really hear about it much because generally it's very safe. We only really know about it when something horrendous happens, and there haven't been that many incidents in the last 50, 60 years. 2 that I can think of. It's a very reliable form of energy. It's not like wind energy or solar power where you're at the mercy of nature. Fission happens at a fairly constant rate. One of the greatest benefits of nuclear power is it reduces our dependency on fossil fuels. Fossil fuels are running out. We are going to run out of them at the rate we're using them. So anything we can do to reduce how much we use them is a benefit. Another incredibly useful benefit is it's clean. There's no sulfur dioxide, so no acid rain. There are no greenhouse gases, so it doesn't contribute to global warming. Also, huge amounts of energy are released from a relatively low mass of fuel. You would need a far greater mass of coal compared to uranium to release the same amount of energy. And another benefit is our planet is rich with uranium deposits. It's very cheap and plentiful. So I'm not going to tell you what you should think about this. It's up to you to decide, but I think it's got some very compelling for and against arguments. So now we can explain how nuclear power works and evaluate the use of nuclear power stations, which could be a 6 marker. So we've looked at fission in some detail because that's how we generate electricity through nuclear power. But what about fusion? Can we not use fusion? What are the benefits and why aren't we doing it? Well, if we compare them, there are some definite advantages to fusion. However, there are also reasons why we're not using fusion currently. Firstly, fission is achieved at room temperature, whereas fusion, as I've already explained, because of the repulsive forces between the positively charged protons in the nuclei, you need extremely high temperatures and pressures to force them together so they stick. Most materials would vaporize at these temperatures, which I said was around 10 million degrees Celsius. So to build a fusion reactor is incredibly difficult and very expensive. By contrast, a fission reactor is much cheaper. Fission reactors, as I've said, do release a lot of heat, but fusion reactors would release more heat for the same mass of fuel. Obviously, we've seen one of the biggest issues with fission reactors is the creation of radioactive waste. This issue would not be the same in fusion reactors because we're not using uranium fuel rods. Of course, fission is already tried and tested, it's currently possible, but due to the expense and the difficulty of building a fusion reactor, it's currently not possible. To contain a fusion reaction, you need a very powerful magnetic field. If you want to have a good idea of what a fusion reactor might look like, try watching the film Spider-Man 2, the one with Doc Octopus in it, because he tries to build a fusion reactor and you can see it all go wrong. In fact, it's a very powerful magnetic field that results in the death of his wife in the movie. So remember, the 3 most important things you need to consider with a fusion reactor is you require very high pressures, very, very high temperatures, and obviously a very powerful magnetic field. Comparing fission and fusion reactors is also something that can be a 6-mark question. That's how you evaluate the use of nuclear fission and fusion as a source of energy.